Alright. Welcome, folks, to the question and answer session of Anna and Linus's talk on their amazing software, or Umbridge. There's a little bit of uncertainty there, but you'll know if you watch the videos. This is the Q&A session. So they have already posted a 20-minute sort of overview, a little bit of lecture style, and then a 1-hour workshop where Anna and Linus show you the various parts of Umbridge, from a very basic single container model all the way up to how to deploy this thing onto a Kubernetes cluster. I have some questions from my end, and I'll start off with those, and then we're going to kick it off to the audience to ask any questions they have. But before I do, as always, I'll just give you folks a moment to introduce yourselves and give the quick 1-minute pitch for folks where this is the first thing that they're seeing. So I'll leave it to you two.
So, Anna, would you like to go?
Sure. Hi, I'm Anne. I'm an assistant professor of computer science at Durham University, and I'm kind of coming from at uncertainty quantification slightly sideways. So I started off doing mostly simulation of various physical processes, heat, and also components of aircrafts which were breaking. And then I started being a lot more interested in how we quantify how certain we are of the predictions of those models. And that's kind of how I came into this.
And I'm Linus. I'm currently doing a postdoc fellowship at Karlsruhe University. And yeah, for me, it's kind of a similar background. So also coming from numerical simulation, moved towards uncertainty quantification. And for myself, a big focus has always been high-performance computing. So trying to get, in this case, uncertainty quantification to run for as large as simulations as I can, and using supercomputers and so on. And Umbridge is sort of the technical foundation that we are now going to use for future research in that direction.
That's great. Okay. So I enjoyed your tutorial and your talk. I had a couple of questions on the more of the technical, let's see, across a variety of pieces. The first one is, you folks are both in academia right now, but your examples included a mix of like tsunami prediction and weather prediction. There was the hurricane, and then beam bending, which for me as a mechanical engineer was quite interesting. In industry where I typically work, when I worked at companies like SpaceX or whatnot, we cared about beam bending because lots of things are beams. Like a rocket is a beam, and if it bends too much, then the whole thing explodes, which is bad. So who do you typically see as the users of your software? Is it folks in academia that are doing research and publishing papers, or are you seeing folks that are in industry quantifying physical processes in like commercial enterprise and things like that? I also ask because the technology you're using is also quite robust between Docker and Kubernetes, right? It's something that you often see more in large-scale deployments in industry and lesser so in a research environment. So curious what the mix is of folks and where this is being used.
Well, I start with the first part of that question and then hand over to you for the second part. I think that's a fair way of dividing it. So we actually have both. So when we started it, we already had a small, is DigiLab a startup? It's a startup, isn't it? Who were there from the start using it. And we have a few other companies as well who use it. But we are also very much kind of integrated in the academic community, which means most of our users are coming from academia. And I think for the second part about the technology, Linus is probably better set to answer that one.
Yeah, I mean, in a sense, I mean, maybe continuing on where Anna left, I would say that this kind of thing that we're in sort of both academic and industry applications is kind of the point behind Umbridge, right? Because we want essentially to make it easier to take state-of-the-art UQ methods, develop those without having to worry about simulation models, about large-scale deployments. And on the other hand, we want to then make that available. So people who actually have simulation problems, like think of the engineer, for example, who would just like to get a number essentially on the certainty of a certain, let's say, rocket not falling apart. To them, we would like to make it just as easy. And the idea is really that Umbridge is sort of the link between the two. And I think that also pretty much leads to the point of why we need this kind of modern software architecture, which we don't see that much in scientific software, I think, because it gives us precisely that flexibility to link the two and on the one hand separate concerns, on the other hand have a unified interface so experts from all aspects of this can easily work together, no matter what their respective background is.
Thank you. Thank you for that answer. For the folks, I don't know if I mentioned this, but the folks in the attendee list, if you'd like to ask a question as well, feel free to use any one of our number of mechanisms. You could raise your hand and I can click the allow to talk button. You could use the Q&A or the chat. Jump in whenever you'd like. Okay, so the next question I have is how large have you seen this scale up? So the first part of the tutorial was, a 1 or 2 Docker containers, but then you go in and you talk about how this can scale on Kubernetes clusters. The first is just, how big have you seen the scale up? And then when people are deciding to use this framework, what heuristics can you give them for how large they need, how large of a cluster size they need for their problem?
Can we split it again? So currently the largest example we've run is actually the tsunami example. And we ran that on 100 of the large compute nodes that GKE provides, which I think makes that 3,200 virtual CPUs in total. Linus, please correct me if I'm misremembering. I think that's right.
I think that's about it. Yeah.
So that's the very largest that we've done so far, at least in the cloud. And that particular example is one we ran before that on a supercomputer without Umbridge, which kind of kicked off our process a little bit in wanting to make that easier, because there we had to really think about the machine we were on and how to port it over onto that particular machine. And you don't want to have to do that every time you run somewhere new. So we're quite pleased with where we are. And I think that Linus is currently working on running on one of the largest machines in the US now, right?
Ooh,
Yeah, so that's actually a project where we've got some access to Frontera, which is at Texas, I think. And yeah, this is very much not a Kubernetes system. So in sort of opening a second track, I think we also mentioned in the tutorials, on the one hand, yes, we have this support for cloud systems, but also we're now working on support for more, well, let's say, traditional supercomputers. The reason for that being, by the way, to some degree, just funding, because we coming from the academic side, typically don't get easy access to the funds we need for running on cloud systems, but we get access to supercomputers that are essentially run by existing institutions where we can apply for resources, right? So this is actually a surprisingly administrative reason for that, but still, I mean, I guess it's good to have both options in either case. So so moving on to the point of what kind of scale should you expect? Unfortunately, I think this has to be a very big depends. So there's really 2 aspects. One of this is your simulation model. Of course, if you have sort of an uncertainty quantification problem that is kind of similar, same number of parameters, same smoothness of your parameter to observable forward operator, you want the same kind of accuracy, the same kind of statistical information, but you replace the model by something that takes 2 times as long to compute, then that doubles the amount of resources you need, obviously. And on the other hand, on the UQ side, it really depends exactly on all these properties like dimensions, smoothness of your forward map, and so on. How many simulations runs you actually have to do for very specific methods. So I think, unfortunately, I have to say we'll just have to try. On the other hand, maybe to sneak in a selling point for Umbridge is you can start testing small, like as you say in the very beginning, you just have maybe 1 model instance and 1 UQ code, and you can just figure out how long that takes in order to get to a solution. And if you find out that you need more resources, you can, in most cases, just keep your UQ software as it is, move to one of our either cloud or HPC platforms, and scale the whole thing up. And essentially just iteratively find out how far you need to go.
So then if I take the tsunami problem as a case study, then can you talk to the workflow of how did you just start with the biggest cluster immediately with the tsunami problem, or did you work your way up? Because even in the tutorial, you mentioned adding a couple of different parts, right? There's a multi-level method that was mentioned, and then there was another component, which was the GP emulator.
Yeah, we really did build that up over a long time period, actually. So obviously you normally do start kind of on your laptop with a smaller version of your problem, and then move on. So what we started with was the basic model and just being able to run that. So there's already a paper from well, ages ago anyway, where it was just about the single model, no quantifying any uncertainty, nothing. Getting that to run on your cluster is already a challenge. So that was kind of the first step. Then we noticed that if we just run the finest model, it's way too expensive. So the runtime is about 20 minutes on an entire node of 120 CPUs. So you kind of immediately jump to, well, we need some coarse approximation so that we can actually get this down to a feasible runtime, which is where the multi-level idea came from. And then again, there's an entire paper about that one. And then later on, Mikkel Lykkegaard, who's at Digilab, came up with this GP, and we added that to the model as well. So there's many stages, and yeah, you don't jump immediately in.
In the architecture for the GP, by the way, can you talk through the flow of how information went through the system? So you have the original model in one portion, then the uncertainty quantification at 2 levels, and did it then update the GP, which then picked another point that would go? Like, yeah, how did this all fit together?
Yeah, so that's maybe a little bit different than how you'd think about GPs traditionally. So when you just think about the GP as sort of the goal, like building sort of an approximate model, emulator, surrogate, meta model. I mean, there's lots of different names for that. You just want to approximate your model in a fast way. I mean, there's this kind of approach going through acquisition functions, which I think your idea moves towards, right? Like you do a couple of evaluations of the model that you want to approximate. And then the GP is going to give you sort of an estimate of uncertainty of where, in what kind of parts of your parameter space, in what regions do you need to refine. And then there you could start triggering new runs in order to improve your surrogate. However, we don't actually care about the surrogate model. We actually care about the UQ side. So it's in our case, it's still the UQ algorithm that comes up with new parameters to try in order to determine the uncertainty of the result that we're looking for. But whenever we find out that our surrogate is not yet good enough, then the surrogate actually goes back to the true model, does a run, updates itself, and goes back to UQ again. So in that case, it's sort of the GP is not what drives the whole thing, but we use the GP in order to essentially skip costly simulation runs whenever we've already seen a similar parameter before. That's the main point. And whenever our UQ algorithm figures out, well, I'd like to also have a look over there, then the GP will have to see, have we already seen enough parameters in that space? Yes or no? And depending on that, it'll have to go back to the model and do something costly, or it'll just immediately return its approximate answer. Right? But what's really nice about it is that it really kind of slots in the middle, right? Because the UQ software still just cares about, I send off a parameter and I want to get a prediction, or I want to get a model output, an approximate one. Whether this now actually comes from the GP going back to the model and updating, or just from the GP returning an approximation, can be completely up to the GP itself. And the GP in turn doesn't really care about how these parameters are being generated that come in. It only cares about being able to go back to the model and to refine itself if necessary. So it turns out that you've basically got the Umbridge interface twice. And now at that point, you can really start playing microservice as you would do in the software industry, right? And start just plugging things together. And none of these components really has to understand the details of the inner workings of the others. And
Yeah, a big selling point of your talk that I feel is not talked about enough, but it's important is that everything has just this HTTP interface and they can be in their own environments. Because as someone that had to in my earlier life deal with MATLAB on Windows. And now I'm on Linux, but I have to have my own set of Python packaging issues and stuff like that. I can't even imagine what it'd take to get MATLAB and Python to work on the same system well. So the fact that you can put these in the containers and have to plug together over a standard interface in our own environments is quite amazing.
Mhm. That's exactly the reason why I like this one application so much, where we had a literally an existing MATLAB code running on a laptop, offloading simulation runs to a Fortran simulation on a cloud cluster. Imagine getting MATLAB and Fortran to play along. I mean, as you say, it's hard enough with MATLAB and Python.
Horrible. Yeah. All right. That's it for the questions that I had. Did anyone in the room have any particular questions, or are people saving questions for session 2? Okay, I think this is maybe the quieter session. That there's nothing from the audience on this one. I will say if any questions come up, then you're welcome to post them on the discourse. I'll drop the thread into the chat. Honored Linus, is there anything else from your end you'd like to share? Okay, so for anyone watching this recording, this PyMCon session is special in that Anna and Linus have agreed to do 2 Q&A. So there'll be one in an EMEA friendly time, or sorry, an APAC friendly time zone. I think about, well, to you it won't matter because you're watching a recording, but it'll be about 12 hours in our time. So that'll be another video that will probably pre-prend to this one. So I'll leave it to that. On and Linus, from at least myself, thank you so much for these at least 3 pieces of content for folks to get started, and especially the software that folks can use within their own practice, whether it's in industry or academia, to understand all the phenomena around us, whether it's beam bending, tsunamis, or whatever else.
Yeah, thank you for hosting.
Yeah, thank you.